Assalamu alaikum everyone. So the agenda for today's tutorial is exercise 2.3 questions, and so these are the questions which are marked in purple lines from 46 to 53. So let's check it out. Okay, so here is the table for your reference. We already saw this table in our lecture. It shows some properties of special functions, i.e. a a float function and a ceiling function. Okay, so these are some properties of these two functions. Let's proceed to the first question. Okay, so show that the floor of x plus half is the closest integer to the number x, except when x is midway between two integers or when it is the larger of these two integers. So before going to this question, let's recall some previous knowledge. Okay, so what does it mean to find the closest integer to a number, to any real number? Okay, so let's find out what is the closest integer to x, right? Okay, so as an example, let's x is equal to 1 by 2, and we know we can write x as 1 plus 0.2. This one is a integer part of a number x, which we usually denote it as n, and a decimal part which is commonly written as epsilon, right? So we know that for this real number x 1.2, the closest integer to this number is 1, right? Okay, now let's find out the floor and ceiling of this x. The floor of x, i.e. floor of 1.2, it gives us 1, and the ceiling of x, i.e. ceiling of 1.2, it gives us 2. This means that floor function gives us the closest integer when epsilon is less than half, right? Because the answer of floor function gave us 1, and we know that 1 is the closest integer to this given real number 1.2. Okay, now take another example, and this time take real number x as 1.7. Again, we can represent this as the sum of integer part and a decimal part, which is 1 and 0.7 respectively. Okay, now the closest integer to this real number is 2, right? Now take the floor of 1.7. What it gives us? 2, sorry, 1. And the ceiling of x is 2. And this is the closest integer, right? This means floor of x gives us the closest integer when epsilon is greater than half. Okay, so as a brainstorming exercise, the question for you all, what if epsilon is half? So in that case, when epsilon is half, which function give us the closest integer? And the answer is both of them, floor and ceiling. Okay, so in general, when x is given, we can write x as n plus epsilon. So floor of x, which is n plus epsilon floor equals to n, gives us a closest integer for epsilon less than half, right? And ceiling of x give us the closest integer, which is n plus 1, when epsilon is greater than half. Okay, so with these concepts in mind, let's proceed to the question 46. Okay, let's take this question to the next page. Okay, and let's look it to the bottom of the page. Okay. So here is the question. Show that the floor of x plus half is the closest integer to the number x. And we know that now for our previous discussion what is meant by the closest integer to a number x. It depends on cases, which is on epsilon, right? And along with this, we have to prove that this thing doesn't exist when x is in the midway of two integers and when it is larger of these two integers. Okay, so let's visualize this question first. So here is our real line minus infinity to positive infinity, and I am marking just integer on this. What we know that this real line contains all real numbers. I'm just marking integers. Okay, so what this question tells us that whatever x you choose from a real line, and so let's take any real number. I.e. let's this the real number from here. So what question tells us? To show that after picking any real number from this line and take the floor function of this real number with half, this gives us the closest integer to the number x, but it is not the case when x is in the midway, i.e. if I take 1.5, which is the midway of 0 and minus 1, sorry, 0.5 minus, right? So this is the midway. Okay, so intuitively we already seen that okay, whenever I take integer from here or from here, right? So what it gives us, if we take the floor of just only x, it gives us minus 1. Okay, but when I add this half factor to this x, now it depends on x what value gives us the floor function. So mathematically, let x equals n plus epsilon, where n is an integer and epsilon is between 0 and 1. So we have two cases, right? And what are the cases? Let's first take this epsilon is less than half. Okay, in that case, the floor of x plus half equals n plus epsilon plus half, which is n plus epsilon plus half. And since epsilon is less than half, this term becomes 0. Okay, so what we just get is n. And we know that whenever epsilon is less than half, this n is nothing but just the floor of x. And floor of x is the closest integer to x in the case when epsilon is half. This is the closest integer since the closest integer to x. So we prove the first part of the question, which tell us that whenever you take the floor of x plus half, this will give us the closest integer to the real number x. And visually we also see that you can take x from anywhere, right? So like if you take x here or here, okay, or anywhere. But if you take x from the midway, i.e. 1.5, 2.5, in the mid of any two integers, right? This thing doesn't hold, and when it is larger of these two integers, i.e. when you take x from midway or from the thing passing through the midway, anytime, any point passing through the middle. Okay, let's check it out too. So the second case, when epsilon is less than and equal to half, right? Now we know that when epsilon is half, the point is the midway point, and for epsilon greater than half, we get this point as an epsilon, right? Okay, so now x plus half equals to n plus epsilon plus half. Again, this will come n by the property we just showed in the starting table and in our lectures too. Right? So this becomes epsilon plus half. So this is n plus what this thing becomes, it becomes 1 because epsilon is greater than or equals to half. Alright, and this is not equals to n, which is the closest integer, right? This means this thing x plus half is not not giving us a closest integer to x when epsilon is greater than equals to half, or in other words, when the point x is on the midway of two integers and on a right side of the midway. Right. So let's conclude our first question. Now proceed to next question. Okay. So our next question is question number 47, which is again on the same concept. Okay. Show that when the ceiling of x minus half is the closest integer to the number x, except when x is midway between two integers, when it is smaller than of these two integers, i.e., as we see previously, this is our real line. These are the integers. Okay. So whenever you take x from this real line, any x, right, and you take the ceiling of this x with minus half, so right, take any x from this real line like this, and when you minus this with a factor of half, what will you get? We get x minus half here, right? So, and when you take midway of this x of two integers, so this x is here or greater than of these two integers, in that case this property doesn't hold. So let's see. So the ceiling of x minus half equals okay. So it's become n plus epsilon minus half, which is equals to n plus epsilon minus half, right? Now all the thing depends on epsilon. So when we take epsilon greater than half, right, what we get? And plus, since it is greater than half the value, it gives us 1, right? and we know that n plus 1 is the ceiling of x, and it gives us, since epsilon is greater than half, this ceiling gives us the closest integer. Okay, so we proved the first part. Okay, whenever this thing x minus half is the closest integer to the number x, right? But this thing doesn't hold when x is in the midway, i.e. epsilon is half, or when epsilon is less than half, the smallest of two. Okay. So the second case, epsilon is less than and equals to half. So in that case, ceiling becomes x minus half, which is equivalent to n plus epsilon minus half, which further reduced to this term n plus epsilon minus half. Okay, what we get now, since epsilon is less than equals to half, so n plus this factor becomes 0, right? Because epsilon is in minus, epsilon is less than half, so this factor becomes minus. So the closest integer or the ceiling is of this number is 0. It gives us 1. But we know that this thing is closest integer when we take floor, but here we take ceiling, i.e. the term x minus half didn't give us the closest integer to x when epsilon is less than half, or in other words, x is in the midway or the smallest number to the midway number, right? So this ends up our second question. Now go to the third question, which is question 48 in our exercise. And the question is, show that if x is a real number, then the subtraction of floor function of this x with or by the ceiling of x gives us y. If x is not an integer and the same left hand side gives us 0 if x is an integer. Okay, so let's first take x is not an integer. Okay, we know that x can be written as n plus epsilon, where n is an integer and epsilon is in between 0 and 1. And notice that since we are saying that x is not an integer, it means there is another thing on epsilon, another restriction, which is epsilon is not equals to, because whenever epsilon is equals to 0, and we can write x as n plus epsilon, which means x is just an n, which is an integer. So it means x is an integer, but we are dealing with the case when x is not an integer. Okay, so let's take our term ceiling of x minus floor of x, which further can be written as n plus epsilon minus floor of n plus epsilon, which then reduce to n plus epsilon minus n minus floor of epsilon. The factor of n cancelled out. What we are now left with is these two. Okay, now since epsilon is not 0, epsilon is in between 0 and 1, this implies floor of epsilon give us 1, whereas ceiling of epsilon give us 1 and the floor of epsilon give us 0. Okay, so 1 minus 0 gives us the value. Okay, so this is what we have to prove, that if x is a real number and if x is not an integer, so this thing, the ceiling of x minus the floor of x gives us 1. Okay, now the second part is, if this x is an integer, so this left hand side gives us 0. Okay, so here is the second case. Let x is an integer. What does it mean? Now, ceiling of x minus floor of x equals, so if this is an integer, its ceiling is equivalent to itself, minus again, if x is an integer, the floor of this it's also equivalent to itself, so x minus x give us 0, hence proved. Okay, so in the next video or in next tutorial video, we will prove some other question as well. See you in next tutorial.